A simple random sample of birth weights in the United States has a mean of 3,444 grams. The standard deviation of all birth weights is 495 grams. Using a sample size of 75, construct a 95% confidence interval estimate of the mean birth weight in the United States. Since we are creating a confidence interval, we are going to need to find our margin of error. In this problem, we were given the standard deviation of all birth weights. So since we were given the standard deviation of all birth weights, that is our sigma. So our sigma is known, which is our population standard deviation. And our X bar is 3,444 grams. And we want to use a sample size of 75. So our N happens to be 75. So as we go through our steps to write our confidence interval, the first step is to check and make sure that all of our conditions are met. The first thing is it a simple random sample, and they told us in the problem that it was a simple random sample. Is our standard deviation known for our population? They gave it to us of 495 grams. And is our population normally distributed, or is N greater than 30? They didn't say it was normally distributed, but we do know that our sample size is greater than 30. Step 2 is to identify our critical values. And since we have 95% confidence, if we remember back, when we have 95% confidence, our critical value is 1.96. The critical value is 1.96. Now that we know our critical value, we need to find our margin of error. And the way that we find our margin of error is our critical value times the standard deviation of our population divided by the square root of our sample size, which here happens to be 75. We use our calculator and we find out that E is 112.0290462. Now that we have our margin of error, we need to set up our interval. And the way that we set up our interval is we're going to take our point estimate, which is X bar, and subtract E from it. And then take our point estimate of X bar and add E to it. 3,444 minus 112.0290462 and 3,444 plus 112.0290462. When we subtract, we get approximately 3,332. And when we add, we get approximately 3,556 grams. I rounded to the nearest whole number because our mean here was rounded to the nearest whole number. And then the last thing we have to do is state our findings. So we are 95% confident that the interval from 3,332 grams to 3,556 grams actually does contain the true population mean. Part B says using a sample size of 75,000, construct a confidence interval estimate of the mean birth weight in the United States. If we think about this, when we did our investigation in class, we saw that as our sample size went up, our margin of error went down. So we can expect that our interval is going to be a smaller interval and that our e-value, or our margin of error, is going to be less than it was in part A. We already know that step 1 and step 2 are, so I'm going to just start at step 3. And my E this time is going to be 1.96 times 495 divided by the square root of 75,000. We use a calculator and we get that E is equal to 3.542669502. So then for step 4, we are going to create our interval. We're going to take 3,444 and subtract 3.542669502. And we are going to take 3,444 and add 3.542669502. We don't necessarily need all of the decimal points at this point, but it's good to use actual values and not rounded values. So when we subtract, we end up with 3,440. I rounded to the nearest whole number. And then when I added, I got 3,448. And these are grams. Therefore, our confidence interval is 3,440 to 3,448. This interval is much smaller than the one that we got in the previous problem. State our findings. So we are 95% confident that the interval from 3,440 grams to 3,448 grams actually does contain the true population mean. And part C says which of the preceding intervals is wider and why. We already kind of talked a little bit about this in part B, but the interval in part A is wider because the sample size is smaller. Smaller sample sizes are going to result in a less accurate point estimate and therefore a greater margin of error.